Hey, here's another screencast, this one on an example of a related rate problems. I like to call this one speed of a jet airliner. Let me read the problem to you. A jet airliner is flying at a constant altitude of 12,000 feet above sea level as it approaches San Miguel Island. The aircraft comes within the direct line of sight of a Navy radar station on the island, and the radar indicates the initial angle between sea level and its line of sight to the aircraft is 30 degrees. How fast, in miles per hour, is the aircraft approaching the island when it's first detected by the radar instrument, and if the instrument is turning upward, counterclockwise, at a rate of 2/3 degree per second in order to keep the aircraft within its direct line of sight? Let's draw a picture. First, sea level. Let's say the radar installation is here and the aircraft is here. We're told in the problem that this angle of elevation at the moment or at the instant we're interested in our calculation happening is 30 degrees. So that's our first variable. Theta is the angle of elevation of the aircraft. And we're told that the rate of change of theta is 2/3 of a degree per second. What else do we know? We know the plane is flying at a constant altitude of 12,000 feet. So I could sketch in its flight path here, parallel to the sea. What do I want to know? I want to know how fast the plane is moving in miles per hour. So what's the velocity of the airplane? In calculus we learn velocity is the derivative of a position function. So let's put a position function in here. If I draw a perpendicular line here, so that's a right angle, then this distance is the horizontal distance between the plane and the radar station. So that's my second variable, P, the horizontal distance between P, the plane, and the radar station. And we want to know the speed of the plane in miles per hour. So I'm going to measure this distance in miles. Now notice we're given that the angle of elevation is changing at a rate that's written in terms of seconds, and we're going to want to convert that at some point to hours, since we need to have a unit of per hour here. So just file that away. So looks like we want to have a formula that relates theta and p in such a way that when we implicitly differentiate it, we get an expression d theta dt and an expression dp dt, because that is going to be the velocity of our plane. So let's look at our diagram. It looks like the theta here is not inside the triangle that has P as a side, but my diagram has a parallelogram. It is a parallelogram. So the length of this side is also P. So looks like I have a triangle here. It's a right triangle. And I can use right triangle trigonometry here. In fact, it looks like we've got a tangent relationship. But let's do a couple things before we set that equation up. Since I'm interested in the units being miles, let's divide this by 5280. There's 5,280 feet in a mile. So this would be my conversion factor from feet to miles. Now then my feet units cancel, and I'm left with the unit of miles here. So whatever this number turns out to be, this is the height at which my plane is flying, measured in miles. So if P is measured in miles, and the altitude of my plane is measured in miles, now I can set up my formula. So my formula says the tangent of my angle of elevation is 12,000 over 5280, all divided by P. And now I want to implicitly differentiate this. But one thing to point out, and we haven't mentioned this before, is our derivative formulas for the trig functions presume that the variable inside the trig function must be measured in radians. So, looking at the problem, we're told that the angle of elevation of the aircraft initially is 30 degrees. Well, that's pi over 6 radians. And we'll also need to convert this 2/3 of degree per second to radians as well. And we'll do that by using the fact that there are pi radians in 180 degrees. So now this measurement is going to be, the degrees cancel, and we're left with a measurement in radians per second. So it looks like we need more space. Let's take that. We have the tangent of theta is 12,000 over 5280 times 1 over P. So there's two things I want to remark about this. The first is, and I'll write this in a different color. Let's write this in purple. Note, a trig function has no units. The way we define it has no units. Look at the definitions of the trig functions using right triangle trigonometry. No units. What this means is when I differentiate a trig function with respect to its variable, its unit is per radian. So this brings me to the second point I want to make. For the differentiation formulas to even work, the variable in the trig function must be in radian measurement. So two things. When we differentiate trig functions, they have to be in radians, otherwise the formulas don't work. And when we differentiate a trig function, the derivative's unit is in per radian. You know, when we differentiate a position function where position is measured in feet and time is measured in second, then the derivative is feet per second. That's because the position function has units feet. Trig function has no units, so there's no numerator in the unit for the derivative of a trig function. It's just measured in per radian. I'll come back to this. So we have this relationship between P and theta. Let's differentiate both sides. So by implicit differentiation, the left-hand side differentiates to secant squared theta d theta dt equals 12,000 over 5280 times minus 1 over P squared. I'm using the power rule to differentiate 1 over P. And then implicit differentiation tells me I got to put that 1 over, or that dp dt on it. I want to calculate what dp dt is. So I want to isolate dp dt. But before I do that, I want to plug in values for secant squared and 1 over p squared. So secant squared, my angle theta, that's pi over 6 radians. So the secant of pi over 6 is 1 over the cosine of pi over 6. Cosine of pi over 6 is root 3 over 2. So 1 over cosine of pi over 6 is 2 over root 3. Square that, and I get 4 over 3. So this is 4 over 3 times d theta dt. So next we need to find what p is. So I'm going to go over here and do some scratch work. We have our Pythagorean relationship between our angle and our p. And here's our triangle with the side measurements. And note, I'm measuring the side length, this side length of the triangle this way because I want it measured in miles, because p is going to be measured in miles. Tangent of pi over 6 is equal to the opposite over the adjacent, which is 12,000 over 25, 5280. Times p. Solving this for p gives me p equals 12,000 over 5280 times cotangent of pi over 6, not cosine, cotangent. And the cotangent of pi over 6 is the cosine of pi over 6 over the sine of pi over 6, and that's the square root of 3. But plugging this in for p over here, I get 1 over 12,000 square root of 3 over 5280. Square that. dp dt. Let's carry that out another step. We'll put this minus sign up front now. So simplifying this 1 over a square, we get 5280 squared over 3 times 12,000 squared, and dp dt. And you'll notice that this 12,000 cancels with one of the 12,000 downstairs. This 5280 cancels with one of the 5280 upstairs. And I can multiply both sides of my equation by 3, so those 3's can cancel. And now let's solve for dp dt. dp dt is negative 4 times 12,000 over 5280 d theta dt. Let's look at this for a second. What do we have here? The 4 came from this secant squared. And the unit on that, as we talked about, is per radian. This 12,000 over 5280, that's our measurement of miles. Our d theta dt, that's given to us in degrees per second. So what I want is I want the second instead to be measured in hours. And I need to convert this degrees here to radians, because I want it to cancel with that. So what we'll do is this. We will leave these numbers alone. And first we'll cancel the degrees, or we'll translate that into radians. So there are pi radians to 180 degrees. So this conversion factor, the pi radians in my numerator will cancel with the per radians here that comes from the negative 4, or from the 4. And the 180 in the denominator, 180 degrees, that unit will cancel with that. Now we look at the seconds. How do we convert seconds to hours? Well, if you think about it for a moment, there's 3,600 seconds in every hour. You can compute it. So multiplying by this conversion factor, this numerator in seconds is going to cancel with the seconds that comes from this d theta dt. And that d theta dt, the value, is 2/3 degrees per second. If you multiply all this stuff out, you get approximately negative 381 miles per hour. So that's how fast the airplane is moving. And it's negative because it's moving toward the island. The distance between the radar station and the airplane is decreasing. Hence, the derivative of that displacement is negative. And there you go. There's your solution.